Hello, I'm Sumit Kumar. I'm here to present the presentation of our group project, the topic of which is design and simulate a rooftop photovoltaic system to meet all electricity needs of a multi-story car park. Along with me, my group members are Yashodhani Randanu, Hasib Kamran, and Anika Tabassum. Moving on to the further slides of the presentation. Moving on to the contents, as we can see the topics that we have included in our presentation here: introduction, objective, literature review, data and load calculation. So load calculation is specifically mathematically calculated the load requirement at each position in our overall electrical system. Homer Pro and MATLAB software is used for the designing and simulation purpose as well. And we have also described the protection system that would, give the access for a smooth run of the overall electrical system. So moving on to next slide, introduction, we can see that the large percentage of energy is obviously produced by the fossil fuels, but that energy is of course of pollution in nature and is not carbon free. And there comes the concept of renewable energy. So solar energy is one of the best source of that. Uh, if we see the crowded cities, rooftop of buildings that offers a sizable parts is frequently goes underused, and this space can be used for PV solar panel installation. However, the major problem with these panels, specifically in North America, we can say is the snow, because snow does not allow, to directly hit the sunlight on the solar panels and can cover the surface of panels. But yet, after that also, we see that the overall, uh, the production loss is less than 35%, which is recommendable. And what we see other than that is the overall increase in the size of the PV system panels can reduce drastically the installation cost of the overall PV panel system. Now, this is one of the most important point to be considered here. And therefore, the rooftop or parking lot that we consider for our project has a lot of space and the area is not an issue for this analysis. The main objective is to meet the power requirement of the multi-story car park that is located next to the new science building at the Memorial University of Newfoundland. It is to be done by the installation of solar photovoltaic system at the top space of the building. Now, it is to be done by the Homer Pro software, as we know that this software specifically provides various feature and easy access to the data of the GHI data, whether it is the solar data from the NASA prediction of worldwide energy resources based on the 22 years of the past recorded data. So to do that in a certain mathematical way, in a simulated way, we use this Homer software here, as we can see in the figure 2 of the presentation slide. And also the figure 1 shows the exact Google Map location of the car parking that we have considered. And below that, we can see the address and coordinates of the total area, that is 6,904 meters square for the considered location. Now my friend Anika would continue.
Hi everyone, I'm Anika. We reviewed some previous research papers related to our project and presented the key findings here. Firstly, the global status of renewable energy market is illustrated to understand our project's demand and future prospects. Then a thorough assessment of various solar PV technologies such as crystalline silicon, thin films, organic and polymer solar cells, concentrated PV was introduced with research done by N. Bansar. Mansouri Kohestani have found that for a PV system producing less than 5 kilowatt, the installation cost is $26,040 per kilowatt. For greater than 50 kilowatt, the installation cost is around $22,000. We can clearly see that the installation cost decreases with the increase in the size of our PV system. And it makes more sense economically to install solar panels on top of large buildings. TV Christianis with her team has examined the financial feasibility of placement for building owners and grid effectiveness of 4 different type PV systems, including amorphous silicon, cadmium telluride, crystalline silicon, and copper in indium selenide. Wang have used 13 different cities in China in different climatic regions to study shading and power generation effects integrated into energy saving effects in rooftop solar PV systems. According to the findings, the elevated system increased the PV system's overall energy output while simultaneously lessening the amount of shade caused by neighboring structure. It was stated by Weizeng. According to the study by J. Foley, PV systems must be built to endure extreme weather like strong winds and loss of snow to ensure their durability. Rooftop PV systems can dramatically reduce greenhouse gas emissions by replacing fossil fuel generated power and can aid in minimizing the urban heat island effect by offering the shade and lowering the amount of heat absorbed by structures and pavement. It was stated by M. Hawk. We have collected PV potential and solar resource map of Canada from the Government of Canada website before our load calculation. In the solar insolation data, we can see that direct normal insolation was 2.826 kilowatt hour per meter square per day. A specific PV power output was 3.186 kilowatt hour per meter square per day. We have also provided the site info just for a clear picture. To design our PV system for the parking, we only considered indoor and outdoor lights as a load of 4 stories and collected data from the site, which we can see in this table. For the indoor lights, we assumed the car park is operating for 24 hours. Here, peak load equals to power per light fittings into number of light fittings, which is 16 kilowatt. Then total load per day equals to peak load into duty factor into number of duty hours. Here we assume duty factor as 1 and got 384 kilowatt hour. On the other hand, outdoor lights, we got 1.2 kilowatt for peak load and 18 kilowatt hour for total load per day. Finally, total load of lighting was the summation of outdoor lights and indoor lights total load per day, which is 402 kilowatt hour. Now I am handing over the rest of the part to my fellow groupmate Yashodini.
I'm Yashodini and I'm going to talk about modeling and simulation of our proposed system using HomePro software. So before moving into the system modeling, I'll briefly explain about HomePro. So it's a microgrid software by Home Energy and it optimizes microgrid design in all sectors. So what we have to do is we have to provide the exact location we are planning to do the project, and it allows us to download the resource data related to the location and add the system components and simulate and get the optimum results. So let's move on to the system steady state modeling. Solar resource data were important according to the selected site location. The picture shows the downloaded solar resources data, and if you can clearly see that it varies with the month of the year due to the seasonal changes, and the load data were updated and adjusted according to the demand throughout the year, because since we have outdoor lights here, with the weather condition, with the seasonal changes of St. John's, the sunset and sunrise time has a huge variety throughout the year, like huge wide range of variety. So we adjusted the load demand according to that, because outdoor light operating time depend with the sunrise and sunset of the area. Then the main power source, a solar PV system, is added to the system. Since the Homer has the optimizing feature itself, we added different sizes of PV system capacity to a maximum output to get a maximum output, and the prices were provided to according to the current market values. Then a battery backup system was added into the system to protect the reliability of the system, especially during less sunny or rainy days. A generic 1 megawatt lithium ion battery is used for the simulation here as shown in the slide right now. The system was optimized using several capacities as I mentioned earlier in the slides. So 175 kilowatt hour solar system is the most optimized system capacity, which is selected by the Homer optimization tool. it, it's because it minimizes the excess energy of the system. So this figure shows the optimized results of our proposed system. So now let's move into the simulation results. The picture shows the total net present value of the project cost, and we can clearly see that the NPC of the battery is relatively high compared to the NPC of solar system. And in the cost summary, we can see the total NPC is around $1,280,000, and to establish the system we have to spend $775,000. The operating cost is around $39,000, and the replacement cost is around $254,000, while the operation and maintenance cost is around $300,000. So this is also a representation of cash flow of the system. And in generation wise, the total generation from the proposed solar PV system is around 200,000 kilowatt hours in a year, exactly 205,086 kilowatt hours per year. And the total consumption from the lighting load is 146,668 kilowatt hours per year. So the excess electricity is 29.5% of the total generation, and the shortage capacity is 69.7 kilowatt hours, which is like a 0.0425% of the total generation, which is a very good value. The renewable fraction of the system is 100%, and the renewable penetration of the proposed system is 100%. Thank you.
Hi, I'm Asif, and today I'm going to explain the dynamic modeling of our system. So on your right, you can see that there is the Simulink model of our system, and we have the solar panels, we have the PV control, we have the battery management system, the supervisory controller, and the scope from which we can see the graphs and it's working. Right, so in the solar system, we input the irradiance and the temperature, and we also input the total wattage. Then we calibrated the load to its 16.7 value, and then we created PV control and the battery management system. So going into a little detail of the control system, on your right it is the supervisory controller, and it operates all the control system of our system. So the supervisory controller manages all the modes from 0 up till 6 of the control system. So in mode 0, it actually starts the system. In mode 1, the battery is fully charged and isolated. In mode 2, battery is charging. In mode 3, battery is discharging, and up till so on, right? These are all the modes that the supervised controller controls. Moving on to the results of our Simulink model, this graph shows that the solar panel is producing 23.4 kilowatts of power, and the load is consuming 16.7 kilowatts of power. So on your left, the graph shows the mode 2 of our system. So it is when the battery is charging, right? When the solar panel is producing more power than the requirement from the load. So the excess energy can be can be used to charge the battery, right? On your right, that is the mode 3, when the solar power is less and the load is higher. So the battery provides the additional power, so the battery is discharging. This graph shows the mode 5 of the system. So when the solar power is less than the load power, right, the load is more than the solar, so the battery will provide the additional power, right? But when the battery is fully discharged, so the supervisory controller will turn off the system, because the load values can no longer be met from the solar and the battery. This graph shows the mode 6 of the system. It states that when the load is increasing, right, it increases up till like 30 kilowatts. So the solar panel and the battery power combined cannot provide the load power, and it keeps on increasing the load power, right? So then the supervisory controller will turn off the load and isolate it, and the solar panel will only power the battery and it will recharge it. So that is the mode 6. This is the transient response of the system. I just change the load with respect to time, and also the solar panel, the power of the solar, like I change the irradiance values just to check like the response of the system, and just to check if our battery is like charging and discharging at the right time, and just to check the supervisory controller. Whenever we design a system, we also have to make the protection system for it. So for our system, we devise 4 protections, namely the battery protection, the surge protection, the overcurrent protection, and the earth fault protection. Right, for the battery protection, the charge controller regulates the amperes and the voltage that is delivered to the battery. The surge protection basically regulates if there's any electrical surges or like electrical spikes for the system. The overcurrent protection protects the system from like overcurrent, right? And the earth fault protection basically states that all the equipment must be protected. It must be earthified so that it does not like conduct electricity. To conclude, we made a PV system that can fulfill all the energy requirements of a multi-story car park, and we use Homer Pro software, we use MATLAB Simulink, and we also devise a protection system for our whole PV system. And we also emphasize that using rooftop PVs is pretty encouraging for the environment and for the feasibility point of view, because like a company or any building can save a lot of money using rooftop PVs, right? And especially in our case for a car park, like there is exposed roof and there's a huge area, so it is very beneficial. These are all the references that we use for our literature review and throughout the project.